It was a barn burner. They made it in three styles: 10 liter, 10.2, 11.7, and 12 liter single overhead cam. And it made power. And it made gobs of power. And it was relatively clean. Now, volumetric efficiency is the amount of air that the cylinder can hold versus the amount of air we can put in it. Makes sense? So if I've got a cylinder that I can fill 85% of, my volumetric efficiency is 85%. Now there's a lot of things we can do to increase how much air I can put in the cylinder. Air contains what? Oxygen, right? The more oxygen I put in the cylinder, the more fuel I can burn. The more fuel I can burn, the more powerful the combustion event. The more powerful the combustion event, the more pressure is released on top of the piston, the more torque I make. Make sense? Okay. You've all heard of turbos. Turbo is just a pump. And it pumps air into the cylinder above what normally would be put in there. What feeds a non-turbocharged engine? What feeds the air into the engine? What pressure feeds the air into an engine of a car that does not have a turbocharger?
No, atmospheric.
Well, part of
Atmospheric.
atmospheric pressure. Atmospheric pressure. Depending on where you're at, 14.7 here, 12.2 in Denver, right? Which is fine, but as we go up in elevation, we drop in atmospheric pressure. So electronic fuel injected help offset the power loss because we can meter the fuel to meet the air pressure. Turbocharger help because now I'm putting air in the cylinder above atmospheric pressure. What's the term used to describe that?
Forceful injection.
Right answer, wrong question. If I'm forcing air into a cylinder above natural pressure, above atmospheric pressure, what is the term I use to describe that additional air that's going into the cylinder? Boost. That make better sense? What did you say, forced induction? Yeah, that worked. Boost. Boost pressure. So anything going into the cylinder that the turbocharger provides that's above atmospheric, wherever you're at, is called boost. So if I'm putting 18 pounds of pressure in my cylinder, the first 14.7 is atmospheric pressure. So my boost is something like 3.3 pounds. Okay? You've all heard of displacement? 5 liter, 2.3 liter. Back in my day, 327, 427, 426 Hemi, 396, the big boys. Now it's 6.6, 6.7, 3.7, 3.5. This all describes the amount of air that engine moves when all the cylinders make one stroke. How much air it displaces. In nautical terms, when they say the displacement of a ship is 98,000 pounds, that means when they put this thing in the water, it moves 98,000 pounds out of the way so it can ride in the water. It displaces 98,000 pounds of water. Not bad for a Marine that's never been on a ship, eh? We can read. When I talk about a 3.5 liter V6, I'm talking about an engine that moves 3.5 liters of air for all the cylinders, and the engine is in a V configuration. That's a V-configured motor. When I talk about an inline 6, all the cylinders are in line, one behind the other, with cylinder number 1 being at the first cylinder in the front of the engine. Okay? That's an inline motor. Okay? There's certain advantages to each design, but most tractor trailers and most buses run an inline 6. Mechanically speaking, and you could talk to a physics professor, but the inlines produce more torque because of the alignment between the crankshaft and the connecting rod at the time that the expansion on top of the piston takes place. Okay? It's very rare that you would see a V-configured motor in a large Class 8 over-the-road truck. Okay? The only one I know of that makes currently a V-configured diesel is the 5-liter Cummins in the Nissan Titan.
Let's put that in a vote.
Huh?
Let's put that in a vote.
You could. You could. So when we talk about displacement, we'll do a little math here. Bore times stroke. The bore is the size of the hole in the block. The stroke is how far we go up and down in the bore, the distance traveled. Okay? So if I look at the math, we've got to figure out the area of the circle of the hole. So to do the area of a circle, if you remember back in math, pi is a mathematical constant. It's 3.1444 dot. It goes on. So every day you go, you see March 14th, and everybody goes, it's pi day. This is what they're referring to. That's when you've been in math way too long. So what we do to figure the bore of the cylinder is we take 1/4 pi, which is 0.785, times the square of the circle, which is the diameter squared. The diameter of the circle is simply the distance across the top of the circle. That is the diameter, and we square that. So for example, if I've got a cylinder that has a 3-inch diameter, 3 times 3 is 9, times 1/4 pi, I have a 7.065 area in my cylinder. Okay? If my piston travels 4 inches in the bore times the area of the circle, I got 28.26 inches of air that it displaces each cylinder. If I have a 4-cylinder engine and each cylinder displaces 28.26 cubic inches of air, I have 113.4 cubic inch engine. That's how much air that engine in total moves when all the cylinders go one stroke. We good? Don't worry, it's not on the test. He's like, oh, thank God. Okay? So that's the engine's displacement. That's where the 6.7 liters comes from. That's where the 5 liters come from. That's where the 3.5 liters come from. It's 3.5 liters of air the total combustion, the total number of pistons move through the engine in one stroke. We good? Okay. Compression ratio is the sweat volume of the cylinder. It's the amount of air in the bottom of the cylinder when the piston's at the bottom versus how much we compress it to in the space above the piston. Compression ratios. You've all heard of these. Common today, 9.5 to 1. And here's how we get to that one. Increase in compression ratio results in higher degree of compression pressures. This is not a bad thing per se when you talk about performance. Okay? It's the displaced volume of one cylinder divided by the clearance volume. It's the amount of air we got when we start at the bottom and that piston moves up. Now, why do we compress air in the engine?
To heat it up.
What's
To heat it up.
bingo? I need heat. I need heat to support combustion. I use the spark plug as an ignition source to light off my fuel air mixture, but I need the heat in there to keep the cylinder hot so I get an efficient burn and more pressure. Okay? So, using an engine with 7.065 cubic inches in cylinder volume, that's the one we got back here. Diameter times quarter pi gave me the total volume of the cylinder. In this case, it's 7.065. So if I were to take and fill that up, it would be 7.065 square inches. Total volume of the cylinder, right? I measure how much distance is between the top of the piston and the bottom of the head when it's at the top of its stroke. In this case, it's 3/4 of an inch. I divide the area of the cylinder by what's left at the top when I run it all the way up, and I've compressed every 9.5 inches that's in here, I compress it to 1, 9.5 to 1. That's how we calculate the compression ratios. Okay? And most engines these days are about 9.5 to 1. That's what those gas guys are out there. Diesels, 15, 16, 17, 18, 19 to 1 because we need that heat. We good?
Normally, like if I was checking, you put a gauge in, right? You crank it
Yeah.
3 times. So
Yeah, and that'll give you a raw number.
Yeah.
That'll give you 300 pounds, 400 pounds, 500 pounds. That doesn't give you the ratio. That gives you the amount of air it compressed. The pressure it builds when that moves that piston up to the top of the cylinder. Okay? Doesn't give you the ratio. The ratio you have to figure mathematically. Okay? Stretch or question?
Question,
Shoot.
how did you get that number, that 9.5 to 1?
Okay, take your calculator out.
I did, and it's 9.42. What is that? What
Same thing, 9.42.
is, what,
Let's see, I left my phone in the office. 7.065 divided by 7.75. I came up, last time I did our calculator, I came up to about 9.44 something or another. I'd have to check my math.
942.
942, okay.
so
It's a little
it
off.
should be 9.42 to
Well,
1.
if I carried this out, the 3 decimal places that this is, I'd probably can get to that 9.5.
Oh, you're trying just rounding it off.
Yeah, it's a roundup.
Okay,
The important part is the math works.
yeah.
Okay. I bet you weren't this picky in high school when you're in math. You're probably You're probably getting pretty good at figuring Dale ratios now that they're still looking for you, right? All right. So that's your compression ratio. Compares the cylinder volume when the piston's at the bottom of its stroke to the cylinder volume at the top of its stroke. And along with increase in pressure, you have an increase in heat. That's Boyle's law. You want to look, I believe it's Boyle's law. B-O-Y-L-E-S. Okay. Now, rate mean effective pressure. This is now when we get into the hot rod guys. Okay, they look at the average pressure of all the strokes, and they come up with a BMEP number. Now, if that number's way off, that means the engine's not efficient. And there's ways to change the pressures. If there's so much pressure required to exhaust the air out of the engine, if I'm exhausting the air, I'm using power because I'm now forcing the piston to push out spent exhaust gases. And the easier I can make that to get the gases out of the motor, the less power I use to get the gas out of the motor, the more power I can put to the wheels. Headers, tuned toward exhaust. Okay? The less effort I have to use to draw air into the engine, the more effort I can put to the ground. Dual plenum intake manifolds, tuned port injection, turbo. blower. All kinds of things. So these are the average pressures in the engine. It's a paper calculation. When the engineers want to get a certain amount of power out of a certain size engine to meet a specific goal, the SVO 5 liter from the mid-80s. That was a barn burner back then. In fact, Chippies ordered that Mustang because of that Ford V8. They got tired of getting outrun by Camaros, GTOs, Mustangs, because at the time in the 80s they were running the all wonderful Dodge Diplomat. Top speed, 84 miles an hour. I think Datsun 510s will blow the doors off that thing. Chippies got tired of being embarrassed, so they went to Ford. They said, hey, now in this era, we were at the peak of emissions. Peak of emissions. In fact, emissions started back in the 70s. Okay. 1970, Chippies had a 440 cubic inch Dodge Polaris with dual 4-barrels that made 412 horsepower, and it would do the quarter mile on 126 miles an hour in full police gear. It was the fastest production cop car ever made at that time. The next year in smog, that same motor went from 400 horsepower to 174. Top speed quarter mile, I don't know, you had to turn the page on the calendar. Okay, that's how bad it got. So they had to do something. So Ford came up with their infamous 5-liter Mustang motor.
5.0,
5.0, it was a venerable 302. They sent it over to Ford Special Vehicle Operations, the hot rod guys at Ford, and they made this badass little motor. They put it in a Mustang, they put a Chippy Star on the door, and they said, okay, fellas, let's play. And they did. Okay? And the way they got that horsepower out of that 5-liter is guys crushed these numbers until they came up with something that worked. Okay? BMEP was amongst many calculations they had to make. Okay? Cylinder, piston, connecting rod, crankshaft. And you will see those because we will take them out. That's considered, the crankshaft, cylinders, and pistons are considered the bottom end of the motor. The engine. I know my engine guys. It's not a motor, it's an engine. Okay, whatever.
The new buses have a motor.
The new buses do, yes, thank you. The hydrogen buses have a motor.
You'll be getting that.
Traction motor. I like traction motor. That just sounds cool. Oh, we got a traction motor in it. Cool. Okay? So we have to have a certain sequence of events for this internal combustion engine to work. Okay? So on the intake stroke, there's components in the cylinder head we call valves. So we'll get into those when we start getting into components. Typically you have two kinds of valves on this. You have an intake valve and you have an exhaust valve. Okay. How they work we'll get into later, but right now I just want you to understand the sequence of events we need to get to a power stroke. Power. Tim the Toolman Tater, right? Okay. So first thing we do, we got to breathe. Just like you and I, we have to breathe. So the intake stroke, the intake valve opens up, and air and fuel enter the cylinder. Unlike a diesel engine, where straight air would enter the cylinder. Gas guys, well, by the way, there's no diesel questions on this exam. I'm just giving you this for comparison. Additional knowledge at no extra charge. It's like the bond is 16% more for free. Really?
Wait, there's more.
You mean, instead of gas, you mean a carburetor. Gas is injected also.
Yes, it is, but we're beyond the days of carburation, unfortunately. It's actually, well, no, not in ours. On our gas motors, it's more akin to a carburetor than it is an injector. Because we don't inject it in individual cylinders using an injector. We mix it in the intake manifold, and it's fed into the engine. So it's mixed outside of the engine's combustion chambers and fed into the motor. That's where you were leading me to, right? Right, Chris?
Well, you can also have injected also, but now they're in the plant before it goes in the
Yes.
cylinder.
Yes. A direct gas injected motor, yeah, it's still spark plug because it's not using the heat to ignite it. You could with gas, it's not stable enough. It's called pinging. My old man had a Jeep. It was so bad he'd shut it off. We'd come out and still be. He wouldn't even use it. He just turned the key back on it and fire back up. I don't know if that starter ever got used. It was curious. Dad, you gonna do something up? No. Hey, get this, Chris. It was a 1965 Jeep Grand Wagoneer. Okay. With a
305?
no.
283?
No, it had a Willys Overland single overhead cam 6. Overhead cam. We had it in production long before the Japanese. We just didn't do anything with it. It had an oiling problem for the camshaft. That's why it was never really popular. Had they taken the time to fix that problem, because that motor made 300 horsepower factory. Monster carburetor on it. And it had headers, factory. It was geared so low you could pull a house with it. It was an awesome little motor. Everybody thinks, oh, it was a Chevy motor. No, it was a Willys Overland. Anyway, so we got to breathe. So we're going to open the inlet valve and we're going to draw in our air-fuel mixture. Now, anything that affects the breathing of this engine, either the intake of the air-fuel mixture or the exhaust of the spent byproducts, is going to affect the performance of the engine. It's like you trying to run track with pneumonia. Your lungs are not able to exchange oxygen into the bloodstream because of the pneumonia, right? Please don't do this. We're going to catch pneumonia, go run track. I used an example at LA Unified of running track with one of those red straws and only breathing in through that straw. That's a restriction. A guy tried it, he passed out. Dumbass.
He did?
Yes, he did. I got in trouble for that one. Yeah. The point I was attempting to make before this idiot ruined it was any restriction on airflow either into this or out of this motor is going to affect how it runs. So if you've got a dirty air cleaner, if you've got a loose hose clamp, something along those lines where the air that's supposed to go in the engine isn't getting there, it's going to affect how it runs. So on the compression stroke, now the pistons move down in the bore, and it's full of fresh, clean, oxygen-rich air. Power stroke, the cylinder now is moving up. Both valves are closed. And slightly before, we're on the compression stroke. Slightly before we get to the top of its travel, I'm going to light off my spark plug. Now, why don't I wait till it gets all the way to the top? Why do I wait, 12 degrees before I get to top dead center?
So the heat?
What about the
You
heat?
want most of the heat?
Pre-ignition.
Partially, but not the answer I'm looking for. It takes time for the spark to establish itself, the heat to spread, and light off the fuel-air mixture. Right? That has to take time. It doesn't occur instantaneously. So when I light the spark plug, the flame front has to spread across the whole fuel-air mixture in the bore. Then the combustion process has to occur where the fuel is actually combust and the heat energy is released from it, and then it acts on top of the piston to push it back down. Now, if I do it too soon, I get pre-ignition, which is the pressure wave in the bore traveling down the bore as the piston comes up in the bore, and they collide. That's that knock you hear. So to provide enough time for all this to happen, I light the charge off a little early. I light it off light it off in advance of top dead center. When you light something off in advance, you light it off early. So if I have a point in the bore where I light the cylinder off, and I decide to light it off in advance of that, the piston is higher or lower in the bore? Lower. So when I light my ignition off in advance, the piston's lower in the bore. Okay? If I light it off later than I should, now, don't be triggered by this word. Come on, guys. No, you're right. The timing is said to be
A little slow.
yeah, what's the politically correct term? Mentally, never mind. I won't even go there. If I retard the timing, that means I delay the ignition. The cylinder, the piston is going to be up higher in the bore. Oh, developmentally delayed. I can't say retarded. It's timing challenged. This is called ignition timing, and we'll talk more about it. Now, there are reasons I would do both and fire it off in advance. There's a spec, factory spec, that says base timing (12 degrees) before top dead center. Top dead center is the piston's up as high as it's going to go. And so what that means is 12 degrees before the piston gets to the top of its travel, we're going to light the spark plug off, because the engineers have figured it takes 12 degrees of rotation to ignite the spark plug, establish the flame front, combust the fuel air, and release the energy. And by that time, the piston will be at the top of its travel, and then it can be forced down. Right? So if I light it off too soon, let's say there's conditions that when I light it off at its base timing, that process of establishing a flame front stuff happens too fast, and the piston isn't all the way at the top of the bore before that pressure wave is produced, and it strikes the piston as the piston travels up. So I'm going to delay lighting off the spark plug. I'm going to let the piston get a little higher up in the bore so we don't have the pressure wave getting established too early and striking the piston as it travels up. We retard the timing.
It doesn't change by the fuel type too?
No, timing is affected by the fuel type. You have to throw a lot of advance in the ignition for a slower burning fuel. No. Well, to a certain degree. What is octane? I guarantee you're going to get it wrong.
The resistance is it?
Resistance to what?
Ignition.
Reignition. It's the fuel's ability to remain stable under heat and pressure. Everybody thinks, oh, octane's about firing off. You need a higher octane to run your hot rod. Well, you do. Let's say I got my Team Arrow, right? And I take my 9.5 to 1 compression ratio and I jack it up to 15 to 1. That means I'm going to be introducing more heat and more pressure in the cylinder. Well, if I have a fuel that's not real stable, it's going to ignite before the spark plug, and it's going to foul up my ignition timing. So my Team Arrow is going to be basically worthless. I'm going to be sitting on the line. I'm going to blow the doors off this Corvair, which is not a good idea, because they can run. And I drop the throttle and take off, and I get, and I'm like, it's like, whoa, wait a minute. I got this $12,000 high performance Team Arrow motor, and I just got my doors blown off by Wally Cleaver in his Corvair. It's because when you try to throttle up the engine and put it under load, it develops so much heat that the fuel air in the cylinder ignited before the spark plug, and now the piston's trying to come up while pressure's pushing it down. That won't last long. Either blow a hole in the piston or blow a cylinder out the side of the block. Either way, you lose. So I have to have a mechanism to delay the ignition so I don't do that. And it's in the ignition system. It's now all done electronically. Okay.
So the CEGs have the same degree and everything, or?
No. That engine in its diesel configuration will have different base timing than the gasoline equivalent because that gas is a low heat, slow burning fuel. So I got to light it off way early to give it time to combust properly and have the piston in the right position so when it does finally release its heat, the piston's at or near the top and can push it down. That's the problem with back in the day they used to do those propane conversions. You take your truck to Wally's garage and you convert your gasoline engine to propane and it ran like crap. Because all he did was he put a propane cylinder and a propane fuel system on it and sent you out the door with gasoline ignition timing. Now they do it electronically and they're much better at it. Okay? So octane simply refers to the fuel's stability, not how well it lights off. It all lights off the same. It's how much tighter can I squeeze it before I light it off. That's all it is. Now, the guy with the Camaro was correct in that with the higher pressures and temperatures involved in his 15-to-1 motor, he had to have a more stable fuel. High octane. Not because it was any hotter of a spark, had nothing to do with that. Since he's running higher pressures and temperatures, he needed the fuel to be more stable so it would fire off when it should. So he had the idea right, but the wrong reason. Make sense? I remember back in my day, we'd go to the Texaco station and get 100 octane gas. Sure. Pull up on my mom's hot rod AMC Hornet Sportabout station wagon with the straight six at the Texaco Chief. Because I was feeling froggy, I'd dump 100 octane gas in it and spend my 28 cents a gallon. About right? Late 70s? 28, maybe 35 cents a gallon?
Something like 35.
Well, 100 octane, so it's probably a little higher. So you used to be able to get leaded, regular leaded, premium leaded, supreme, and if you're a Texaco, super ethyl. So it was like 90, 92, 94, 100. Okay. So the compression stroke simply does what it says. It compresses my fuel-air mixture. The power stroke, we light off the fuel charge. At the appropriate time, we establish the pressure wave. It pushes the piston down. My valves are both closed. Now what would happen, let's say, on my compression stroke, if I had a wee bit of a valve closing issue? Let's say my valves, when they close, they didn't seal up really good. How would that affect the engine? Or would it? Let me ask you that. Would it affect the engine?
Yes.
How?
Mixture.
Nope.
By fire.
Fuel mixture.
Or
Probably, but you're missing the boat. What would be affected by lower cylinder pressures? How would the power be affected?
Air to fuel mixture.
No. Heat. If I can't build pressure, I can't build heat. Yeah, I'd hear it coming through either the intake or exhaust depending on which valve is leaking. But because I'm trying to build pressure and some of it's leaking off, my cylinder pressures wouldn't be in spec. The heat needed to properly burn the fuel would not be in spec. So I'd get an incomplete burn. So with an incomplete burn, I'm not releasing all of the heat in the fuel. So I'm getting less pressure on top of the piston. Make sense?
Could it be that the valves are not adjusted accordingly?
Correct. That would affect the breathing. If I got to take 3 degrees of rotation, I only have a certain number of degrees of rotation this engine can breathe. Let's say 58 degrees, my valve's going to be open. if I have to spend 4 of those degrees to make up extra clearance that shouldn't be there just to contact the valve, so I'm losing 4 degrees of breathing. So I'm getting less fuel air into the cylinder. I'm affecting its volumetric efficiency. Make sense? Okay. Now, on the exhaust strokes, we have to get rid of the spent or burned or combusted air oxygen mixture, the chemical mixture of the exhaust. So after I reach bottom dead center of the compression stroke, I'm going to start traveling up in my bore. I'm going to open my exhaust valve and I'm going to push the gases out of the engine. Very near the top of that exhaust stroke, I'm going to open both valves, intake and exhaust, for about 18, 20 degrees of rotation, and I'm going to finish pushing out the cylinder gases. Why do I open the intake valve at the very end of the exhaust stroke? And what is that called?
Scavenging.
If it's a 2-stroke?
No.
Valve overlap. Well, why do I do it?
Forcing fresh air in, clearing out the rest of the combustion chamber.
Yep. I'm using a couple of theories here. Thermodynamics is one. Hot air does what? Up or down?
Right.
Cold air does what?
Yeah.
Okay. Can 2 particles occupy the same space at the same time? No. Second law of relativity. So I'm going to use thermal effects of when I let cold air in, it's going to automatically sink to the bottom. And in the process of doing that, it's going to displace the burnt gases to the top, closer to the valve. As the piston continues to move up, theoretically, it should be able to push out all the spent exhaust gases before I open the inlet valve and let in more cold, clean, fresh air. Valve overlap. Okay? How are we doing so far, guys?
Good.
Okay, why don't you guys come back about 10 after 9. And I'll fry your brains some more.
Over easy.
Remember one of my hot rods had a radical cam in it, and the reason it would idle so rough was called valve overlap.